Emulsions are liquid-liquid colloidal systems in which both the dispersed phase as well as the dispersion medium are liquids. An emulsion may be defined as a colloidal dispersion of two immiscible or partially immiscible liquids, in which one liquid acts as the dispersion medium and the other as the dispersed phase. In most emulsions, one of the liquid is water, while the other is a hydrocarbon and is referred to as oil. Depending on the nature of the dispersed phase, emulsions are broadly classified into two types. They are oil and water type emulsions and water and oil type emulsions. In oil and water type of emulsions, oil acts as the dispersed phase and water acts as the dispersion medium. For example, milk is an emulsion of liquid fat globules dispersed in water. Another well-known example is that of vanishing cream. In water and oil type of emulsions, water acts as the dispersed phase and oil acts as the dispersion medium. For example, butter is an emulsion of water dispersed in fat. Other common examples of this type are cod liver oil and cold cream. Emulsions are generally unstable and separate in two layers on standing. Thus, to stabilize an emulsion, small quantities of certain other substances called emulsifiers or emulsifying agents are added. Emulsifying agents stabilize an emulsion by reducing the interfacial tension between the two phases. Proteins, gums, natural and synthetic soaps, detergents, etc. are the principal emulsifying agents for oil and water type of emulsions. Similarly, heavy metal salts of fatty acids, long-chain alcohols, lamp black, etc. are used for water and oil type of emulsions. Emulsions exhibit properties similar to colloids, like the Tyndall effect, the Brownian movement, electrophoresis, coagulation or de-emulsification on the addition of electrolytes, and so on. Emulsions can be diluted by adding any amount of the dispersion medium, that is, water for oil and water type emulsion and oil for water and oil type of emulsion. On the other hand, if the dispersed phase is added to an emulsion, it forms a separate layer. An emulsion can be separated into its constituent liquids by boiling, freezing, centrifuging, electrostatic precipitation, etc. A well-known example of centrifuging is the separation of cream from milk. Finally, let's see some important applications of emulsions. A large number of pharmaceuticals in the form of lotions, creams and ointments, which are oil and water or water and oil type of emulsions, are prepared to facilitate easy absorption by the body. The cleansing action of soap is based upon the formation of an oil-in-water emulsion. The concentration of ore by the froth flotation process is based upon the treatment of the powdered ore with an oil emulsion. Milk, which is an important constituent of our diet, is an emulsion of liquid fat droplets in water. The digestion of fats in our body takes place by the process of emulsification. Asphalt, emulsified in water, is used for building roads without the necessity of melting the asphalt. Colloids play a very important role in nature and in our daily life. The food we eat, the clothes we wear, the wooden furniture we use, the houses we live in, the newspapers we read are all largely composed of colloids. Let us now discuss some important applications of colloids in day-to-day life. Have you ever wondered as to why the sky appears blue? The sky is the empty space around the earth and has no color as such. It appears blue due to the scattering of blue light by the dust particles and the water suspended in the air. Seawater also looks blue for the same reason. The colloidal impurities in seawater scatter blue light. The Tyndall effect of scattering of light by colloids is responsible for the blue color of the sky and the seawater. Do you know that some of the food we eat is colloid? Milk, halwa, butter, ice cream, fruit juices, jellies, etc. are colloids in one form or the other. For example, milk is an emulsion of fats in water, while ice cream is a dispersion of colloidal ice particles in cream. Another very important colloidal solution is blood. Bleeding from a fresh cut can be stopped by applying a concentrated solution of ferric chloride or potash alum. The negatively charged colloidal particles of blood get neutralized by the ferric or aluminium 3+ ions, resulting in the coagulation of blood. Fog, mist, and rain are all colloidal in nature. In winter, at night, the moisture in the air condenses on the surface of dust particles, forming tiny droplets. These droplets, being colloidal in nature, float in the air, forming mist or fog. It is interesting to note that even clouds are colloidal systems. Clouds are aerosols consisting of small droplets of water suspended in air. Due to condensation in the upper atmosphere, the colloidal droplets of water grow bigger and bigger in size till they come down in the form of rain. It is worth noting that a natural disaster of cloudburst is believed to occur due to the mutual discharge of oppositely charged cloud particles. A cloudburst results in a very heavy downpour in a short period of time. We also come across the term artificial rain. Clouds, as we now know, are colloidal, carrying some electrical charge. Clouds can be made to cause rain by spraying oppositely charged colloidal dust or sand particles or precipitates of silver iodide over them. The neutralization results in coagulation of the water droplets, which come down in the form of rain. This type of rain is called artificial rain. Another interesting example is the formation of a delta at the mouth of a river when it meets the sea. River water is a colloidal solution of sand and clay, which carry a negative charge. Seawater contains a number of electrolytes of sodium, magnesium, and calcium. When river water comes in contact with seawater, the positively charged ions of the electrolytes coagulate the negatively charged colloidal particles, which settle down. The level of the riverbed rises, forcing the stream of water to split. This happens again and again, and over time, the river takes the shape of a delta. A noteworthy example you are already familiar with is the cleansing action of soaps. Soap solutions are colloidal in nature. They remove the dirt and oil particles either by adsorption or by emulsifying the greasy matter sticking to cloth. Let us now look at some industrial applications of colloids. The most important industrial application of colloids is the Cottrell smoking precipitator. Smoke is a colloidal solution of solid particles such as carbon, arsenic compounds, and dust. Smoke from industries is a major air pollutant, and therefore it is desirable to precipitate it to prevent it from spreading. The Cottrell precipitator precipitates smoke on the principle of electrophoresis. Smoke is allowed to pass through a chamber with a number of metal plates. These metal plates are attached to a metal wire connected to a source of high potential of about 30,000 volts. The charged particles of smoke get attracted by the oppositely charged electrodes or metal plates and fall to the bottom after getting discharged. The clean hot air passes out through the chimney, thereby reducing pollution. Another important application of coagulation of colloids is the purification of water. Water from natural sources often contain impurities that are colloidal in nature. Precipitating these colloidal impurities can be carried out by adding certain electrolytes like potash alum or aluminium sulfate. The negatively charged colloidal particles of the impurities get coagulated by the action of the aluminium 3+ ions furnished by the electrolyte and settle down. Pure water can then be filtered or decanted off. Yet another application of colloids is in medicines. Colloidal medicines are more easily assimilated by the body system as they can act over a large surface area. Therefore, they are more effective. It is for this reason that a large number of pharmaceutical preparations are emulsions. For example, milk of magnesia used for stomach disorders. Cod liver oil and skin ointments are all emulsions. Some important salts that are commonly used as medicines are argirols, a silver metal sol used as an eye lotion. Colloidal antimony used for curing chalaza. And colloidal gold used for intramuscular injections. It is important to note that antibiotics are usually injected into the body in colloidal form. Another industrial application is in the leather tanning industry. Raw skin hides of animals contain positively charged colloidal particles. When a hide is soaked in negatively charged tannin and compounds of chromium, mutual coagulation takes place in the pores of the hides. This results in the hardening of the leather. The process is called tanning. The principles of colloids and interface signs are used for the successful formulation and manufacture of photographic products. The color-forming components are usually delivered in colloidal form. Photographic plates and films are prepared by coating an emulsion of light-sensitive silver bromide in gelatin over a glass plate or a celluloid film. Another application of colloidal salts is in the rubber industry. Latex obtained from rubber trees is an emulsion consisting of negatively charged rubber particles in water. Rubber is obtained by the coagulation of latex. This coagulated mass is later subjected to vulcanization and is sold as rubber. We have discussed a number of applications of colloids in life and in industry. Furthermore, inks, paints, lubricants, synthetic plastics, cement, smoke screens are all colloidal solutions. Sewage disposal also makes use of the phenomenon of electrophoresis, as sewage water is colloidal in nature.